Okay, so it's now time for the third talk of the session. We will now hear a presentation on a work in progress paper. The talk will be given by Daniel Pekarek from JKU Linz, and the talk is titled Extraction of Virtual Machine Execution Traces.
So, I am Daniel Pekarek, and I will talk about a debugging technique. Imagine you are developing a virtual machine or an interpreter, and it kind of works already because you can run small programs, but if you run something bigger, you run into problems, something crashes, it doesn't really work as intended. Now the question is, how do you debug this? Because, as I said already, it's already a bigger program. So your first idea might be, let's single step through this in a traditional debugger, but this won't really work because you might have to step through hundreds of thousands of virtual machine instructions, and you don't even know what you're looking for, so you cannot set breakpoints either. So this is definitely not going to work. What would be very useful, though, if you could debug the guest code and simultaneously debug the virtual machine code, because then you could step through the guest program until you find the fishy behavior, and once you found the suspicious behavior in the guest program, you could then continue debugging the virtual machine from there on, because now you know where something interesting happens. And this is precisely what we implemented here. But we went one step further. We used an execution trace-based system, because once you used a time travel debugger, you never want to go back to traditional debuggers. And we use the trace view system. It's an architecture agnostic execution trace-based analysis system. And the idea is you record the execution trace of your virtual machine. There are many different ways how to do this. I won't go into detail, but the point is, once you have an execution trace file, you load it into trace view. And then there is an architecture module. It decodes the individual events from the execution trace file, transforms them into an architecture agnostic representation, and then there is a bunch of analysis algorithms which derive new information, like, for example, the current memory contents for any point in time, and so on. And this generates internal data structures, which you can then inspect from a user interface. And our technique is essentially a new analysis algorithm. So we consume the stream of events, we transform them, and essentially we derive an execution trace of the guest program. And then we put that into a new instance of trace view, which again applies analysis algorithms and so on. And since we derived one execution trace from the other, we can also link the events. So when we navigate through the guest execution trace, we automatically navigate through the virtual machine's execution trace too. What does this look like? Essentially like a debugger, with the main difference we can navigate through the program run in any way we like, and we see an actual execution trace instead of the program code as it's stored in memory. I won't go into more detail. You can play around with this. The code is open source anyway. But the question is, how does our transformation work? First of all, we inspect all the events from the execution trace. Question is, which events do exist anyway? For example, memory accesses. Whenever the program accesses a memory location, this is an event. Or whenever the program executes an instruction, it's also an event. And essentially, we inspect those events and check if there is something interesting going on. And if we find an interesting event for our transformation, we can collect data over time, because maybe we have to see more than one event. And once we have collected all the necessary data, we can create a new event, which then is an event from the guest program's execution trace. So essentially, it's like virtually instrumenting our program in an offline way. And what does this look like in practice? Let's imagine we have a very, very, very simple virtual machine. Initially, we'll allocate some memory for the guest program. We load some program code, and then we single step through the program in a while true loop. And single stepping means we load an instruction word from memory and decode and execute it. So our first transformation rule like virtually inspecting the program is we will look at this malloc instruction because it allocates the guest programs essentially heap. And we will just remember the address of this memory region. We will need it later. And the second rule we will need is whenever the instruction is executed, we will generate an event in the guest program's execution trace. And this will probably contain the instruction word, probably also the program counter and other architectural state. And the final rule we also need, whenever we see a memory access and it falls within the region of the guest program's memory, then we will also keep it, otherwise we will discard this memory event. And this is where we need the value we stored in step 1 to figure out if it's a memory part of the guest program. And essentially these 3 rules are then used to filter the execution trace of the virtual machine, and I hope you can see how this will eventually result in an execution trace of the guest program. Of course, there are many limitations now. What if we have compiler optimizations like inlining or loop unrolling and so on, which would make it a lot harder to write a rule which inspects an event from a certain source code location of our virtual machine. Luckily, we developed the virtual machine ourselves, so we can just disable this if necessary, if it makes problems for us. Second problem, we have this fancy way to distinguish guest memory from the virtual machine memory, but what if there is no such distinction in the virtual machine anyway, like for example in CPython, where everything is just in a virtual machine heap? Well, then we can just pretend we have just one memory area. We don't get the nice separation, but the approach still works. We just get less information in the end. Bigger problem if we have a just-in-time compiler, we get machine code. We don't have nice bytecode or IR, so we don't get a nice high-level execution trace anymore from the guest program. But it's still useful because we can still separate this and purely look at the guest program code, so we don't have to step through a lot of virtual machine code. And finally, what if we have some complex intermediate representation, like for example a GRAL, like in an graph, like in an AST, for example? Then writing rules is still a lot harder. We can still do it, of course, but yeah, it's just more work. And future work, I didn't mention it so far. Right now, the implementation, or for the implementation, you have to manually derive addresses and register names and so on. Would be very useful to just use debug information so we can symbolically resolve source level variables from our virtual machine. It's just not implemented so far because it's a lot of work to do that. This would also give us a high level source level debugging for the virtual machine in the end. Another future work piece is right now the trace tool is purely intended for register machines because it was originally developed to debug low-level interpreters, but a lot of programming language virtual machines use stack machines internally, and it would be very useful to have a direct support for this in the system. And finally, this approach also applies to actual hardware because you can simulate your virtual CPU, RTL simulation, and you would get a simulation trace, and a very similar approach would apply there too. And yeah, that's it from my side. Questions?
Any question?
Hello, thank you for your talk. I'd like to ask you about the kind of rules. You put up 2 or 3 rules there at the start that you're going to impose on your system. Are those rules all to be designed by an expert, or could you imagine a machine learning system somehow synthesizing rules for you to make interesting analyses?
The problem is you have to know what you're looking or what you want to look at, because you probably developed your virtual machine and you know what it means to execute an instruction in the system. So I guess you will have to write this somehow yourself. But in practice, if it's a bytecode interpreter, this is usually very simple to write.
Okay. Could you imagine a sort of templated library of rules that you could pick from if you were using this system with a fairly standard interpreter, or does that not make sense?
I mean, right now it's kind of like this anyway.
Okay.
But in the end, in the paper I described a PowerPC interpreter, a very simple one with transformation rules, and I think there was no rule longer than a few lines of code, so I'm not sure if you really need templates for this.
Okay. Thank you.
Any other question?
Thank you. I'm wondering if you could give an idea as to the latency and the overall user experience and the user interface once you add extra work of processing the trace events?
Once all the data is loaded into the tool, it's extremely fast because there is a big limitation right now. Everything is loaded in memory. The real limitation is you need a rather short trace or a lot of memory to process it.
I see. Thank you.
But other than that, it's almost instantaneous navigation through the trace.
Very nice.
Could you give us a coarse idea of how large your trace files get or how fast they get large?
Depends on the program you traced, of course, but they get very large, very big, because one problem here, or idea here, was it's a complete execution trace with all instructions that were executed and all memory access and so on, because you want to debug the virtual machine itself. And there are other ways how to debug this too, so the system itself does not apply some fancy compression and so on. And essentially, I think 60 million instructions is something like 4 gigabytes of execution trace, and you need something like 32 gigabytes for analysis then. So it's extremely large.
16 million CPU instructions.
Yeah, exactly.
Okay, that's quite much memory that you need.
So it seems generally like you talked here about an offline debugging where you take a trace and then process it. Would it be possible to use similar principles for a debugger that steps through the program as it's running, you know, and potentially save memory that way, or is that not possible for some reason?
Also possible, we just didn't do it. And essentially what we do here is kind of like dynamic instrumentation anyway, but we do it offline. You could do that too, but yeah, we just didn't do it.
Any other question?
Thank you. You said this is open source, but when I look on GitHub, I see other TraceView things, but I don't, under your ID, but I don't see a TraceView itself.
It's linked in the paper.
Okay.
At the end of the paper.
Any other question? Then I think we can take the speaker one more time.